The rules of physics shatter where matter is crushed beyond recognition. This is the domain of ultra-dense cosmic regions, realms like black holes and neutron stars where reality itself is rewritten. By the end of this journey, you will see the entire universe through a new and startling lens. What strange fate awaits a star falling into a black hole? And what bizarre substance lurks inside a dying neutron star? How does it feel to stand at the edge of a reality where time and space lose all meaning? The sheer power of these cosmic regions comes from a simple yet staggering idea. An enormous amount of stuff is squeezed into a space that is unbelievably small. Think of our entire sun, a colossal sphere of hot plasma over 1 million times the volume of Earth, suddenly being crushed down to the size of a city. That incredible compression is what we mean by ultra-dense. In such a place, gravity stops being just a gentle force that keeps your feet on the ground. It becomes the absolute ruler of reality, overwhelming every other power in the universe. This is the domain of the most famous cosmic monsters, black holes, where gravity's grip is so final that it swallows light itself, creating a point of no return from which nothing emerges. And it is the realm of neutron stars, the glittering cinders left after a giant star's explosive death. A single sugar cube of material from a neutron star would weigh more than every person on Earth combined. These are not just distant curiosities. They are the ultimate testing grounds, natural laboratories where the rules of physics are stretched to their absolute breaking point. By studying how matter behaves in these extreme environments, we are forced to question everything we think we know about the fundamental nature of reality. Gravity's power in these places is absolute, a force that rewrites the rules of existence itself. It begins by bending the very stage upon which the universe plays out, the fabric of space and time. Picture a heavy ball resting on a stretched rubber sheet, creating a deep well. Now, replace that ball with a collapsed star, and the well becomes a bottomless chasm. This is the environment surrounding a black hole, where gravity does not just pull. It fundamentally reshapes reality. The most dramatic display of this power occurs at the event horizon, the point of no return. An object falling toward this boundary experiences something profoundly strange, a process scientists call spaghettification. The pull of gravity on the side of the object closer to the black hole is exponentially stronger than the pull on the far side. This difference in force stretches the object into a long, thin stream of particles, like a piece of cosmic taffy. But this is far more than a visual effect. This incredible tension overpowers the very forces that give matter its structure. The electromagnetic bonds that hold your body together, that keep the atoms in a table from simply flying apart, are utterly insignificant here. Gravity rips those bonds apart, dismantling familiar matter atom by atom. What was once a complex asteroid or even a star is reduced to a thin, hot stream of subatomic particles, a form of matter that is entirely alien to our everyday experience. This transformation reveals gravity's ultimate role, not as a gentle tether, but as the master architect of entirely new states of being. And if this is what happens on the approach to a black hole, the question of what lies within its deepest heart is even more unsettling. Once matter crosses that final boundary, our understanding of physics reaches its limits. The journey inward is one of violent transformation. Long before it reaches the point of no return, matter is caught in a furious whirlpool known as an accretion disk. Here, gas and dust spiral at nearly the speed of light, creating immense friction that heats the material to millions of degrees. This superheated plasma glows with an unimaginable fury, emitting blistering X-rays and gamma rays that we can detect from across the galaxy. It is the last bright scream of light before the great silence. Then it crosses the event horizon. According to our best understanding of gravity, Einstein's general relativity, the story ends here. All that mass, the remains of stars and gas clouds, is relentlessly pulled toward the center. The theory predicts it is crushed into an infinitely small point, a singularity of infinite density where the very concepts of space and time cease to have any meaning. But infinity is a concept that makes physicists deeply uneasy. Our other great theory of reality, quantum mechanics, suggests this cannot be the final answer. It implies that some unknown form of pressure or structure must halt the collapse, preventing true infinity. So, does the matter vanish into a dimensionless point, or does it become something else entirely, a strange new state of existence that our current science cannot describe? This is the heart of the greatest conflict in modern physics. The serene rules of gravity that govern the cosmos and the chaotic, probabilistic rules of the quantum world meet in this ultimate arena, and they give completely different answers. The fate of infalling matter is not just a cosmic curiosity. It is the key that might one day unlock a deeper, unified theory of everything. While a black hole represents gravity's ultimate victory, another cosmic remnant fights back with a strange and powerful force. This is the neutron star, a celestial object so dense it defies every instinct we have about matter. Born from the violent death of a massive star in a supernova, what remains is not a void, but a city-sized sphere of the most incredible substance in the universe. In the final moments of that collapse, the pressure becomes so unimaginably intense that it forces a fundamental change upon the atoms themselves. Electrons are slammed into protons, and the two opposing particles merge, canceling their charges to create a sea of nearly pure neutrons. This is degenerate matter, a state governed not by the chemistry we know, but by the bizarre rules of quantum physics. The result is a density so extreme it is almost impossible to picture. A single teaspoon of this neutron-rich material, if you could somehow bring it to Earth, would weigh billions of tons. It would possess the mass of an entire mountain, compressed into a volume you could hold in your hand. This impossible density is held in a fragile balance by a ghostly force known as quantum degeneracy pressure. This is not a force you can feel like a push or a pull. It is a fundamental refusal, a consequence of the Pauli exclusion principle, which states that no two identical particles can occupy the same quantum state. In simpler terms, the neutrons simply have nowhere left to go. They are packed together so tightly that they resist further compression with unimaginable strength, creating an outward pressure that fights a constant battle against the star's own immense gravity. It is this quantum standoff that prevents the neutron star from collapsing further into a black hole. Yet, the true mystery lies even deeper, sealed within the star's hidden core. We do not know the ultimate fate of matter under such relentless pressure. Theorists suggest the neutrons might break down into a superfluid, a frictionless liquid that flows without any resistance. Others propose a solid crust of exotic, ultra-dense elements, or perhaps a soup of free quarks, the fundamental building blocks that are normally forever locked inside particles. Neutron stars are therefore not just inert cinders. They are active cosmic laboratories, their very existence testing the limits of the strong nuclear force. By studying their pulses and ripples, we are trying to read the secrets of matter pushed to its absolute edge, secrets that could completely rewrite the textbooks on nuclear physics. This quantum standoff inside a neutron star is only the beginning. Within the crushing densities near these cosmic objects, the ordinary rules of physics are turned upside down, and reality begins to operate on a different set of principles entirely. Here, quantum mechanics is not a subtle influence. It is the dominant force, producing behaviors that seem to defy logic. One of the most startling of these is quantum tunneling. In our everyday world, if you roll a ball towards a hill, it needs enough energy to reach the top and roll down the other side. Without that energy, it simply bounces back. But in the quantum realm, a particle can simply appear on the other side of the hill, as if it passed through an invisible tunnel. This is not a theory. It is a fundamental process that happens constantly in the cores of neutron stars and at the edges of black holes, allowing reactions and particle movements that would otherwise be utterly impossible. This bizarre behavior is supercharged by another titanic force. The magnetic fields around these objects are almost beyond comprehension, often measured in the trillions of times the strength of Earth's own magnetic field. In this environment of unimaginable density and magnetic power, the fabric of empty space itself begins to stir. According to quantum theory, what we perceive as a perfect vacuum is not truly empty. It is a seething sea of potential, where pairs of virtual particles and their antiparticles constantly flicker in and out of existence, usually annihilating each other too quickly to be detected. But near a black hole's event horizon, the immense gravitational pull can tear these particle pairs apart before they can vanish. One particle falls into the abyss, while the other escapes into space. This steady trickle of escaping particles, a process known as Hawking radiation, slowly saps the energy, and therefore the mass, of the black hole itself. It suggests that even these cosmic titans are not entirely eternal. These quantum effects are not minor curiosities. They are absolutely essential to the stability and the ultimate fate of the universe's most dense objects. The fact that a black hole can slowly evaporate through a purely quantum process, and that a neutron star is held up by quantum pressure, tells us that the smallest rules and the largest forces in the cosmos are inextricably linked. This delicate interplay between the quantum world and the force of gravity is the greatest unsolved puzzle in physics, a frontier where our current theories clash and where the next great discovery about the nature of reality is waiting to be found. The universe's clock is not synchronized. In the crushing grip of a black hole, time itself begins to falter, stretching and warping in ways that defy our everyday experience. This is the profound reality of gravitational time dilation, a direct prediction from Einstein's theory of general relativity. Picture two identical clocks, both perfectly accurate. You place one here on Earth and send the other on a journey toward an ultra-dense object. From your distant, safe vantage point, you would watch in astonishment as the clock near the black hole ticks slower and slower, its hands appearing to nearly freeze as it approaches the point of no return. For the object itself, time would feel perfectly normal. Its fall would continue, but to you, the outside observer, its descent would seem to stretch into an eternity. This is not an illusion or a trick of the light. It is a fundamental property of the cosmos, where gravity does not just bend space, but also twists the very fabric of time. This bizarre effect leaves a direct fingerprint on the light that manages to escape these regions. As photons struggle against the immense gravitational pull, they lose energy. To our instruments, this energy loss manifests as a dramatic shift in the light's color, pulling it down toward the red end of the spectrum. The light from a searingly hot accretion disk, which should be a brilliant blue-white, reaches us as a deep, tired crimson. This gravitational redshift is a direct signal, a cosmic message telling us that time is flowing at a different rate there than it is here. It means that when we observe a flicker of X-rays from a distant neutron star or the final glow of matter spiraling into a black hole, we are not seeing the event in real time. We are witnessing a slowed-down, distorted version of reality, a recording that has been fundamentally altered by gravity itself. To truly understand the violent processes at work in the cosmos, we must first learn to read this complex signature, to decode how gravity has stretched time and shifted light before that information ever reached our telescopes. This realization forces us to ask a deeper question. If gravity can so profoundly alter our perception of time and light, what other fundamental properties of reality might be rewritten in these extreme environments? This paradox strikes at the heart of what we believe is possible. Every object in the universe, from a single atom to a sprawling galaxy, is defined by information. The specific arrangement of its particles, its energy, its spin, all of this data is like a cosmic barcode that makes that object unique. The fundamental laws of quantum mechanics insist that this information can never be truly erased. It can be scrambled, transformed, or hidden, but it must always, in some form, persist. A black hole presents a terrifying violation of this sacred rule. When matter crosses the event horizon, it appears to be permanently deleted from our universe, along with all the information that described it. This is the information paradox, a glaring contradiction that has divided physicists for generations. If our most trusted laws of physics are correct, then black holes cannot exist as we understand them. And if black holes do exist, then our most trusted laws of physics must be incomplete. One radical proposal suggests the solution is not found in the black hole's dark interior, but on its shimmering surface. The holographic principle imagines that all the information about what fell in is not lost. Instead, it is encoded in a scrambled, two-dimensional form on the event horizon itself, like a cosmic fingerprint pressed into the surface of the point of no return. The three-dimensional reality of the objects that fell inside is projected from this two-dimensional shell, meaning our perception of a deep, voluminous universe might be an illusion, a hologram born from data stored on a distant boundary. Another, more violent solution is the firewall hypothesis. It proposes that the event horizon is not a smooth, empty space. Instead, it is a blistering wall of energy, a literal firewall that would instantly incinerate anything attempting to cross. This would resolve the paradox by ensuring the information is never truly lost inside, but is instead converted into pure energy at the boundary. Yet this idea creates its own profound problems, directly contradicting Einstein's prediction that someone crossing the event horizon should feel nothing unusual, a concept known as the no-drama principle. So, is the event horizon a silent, smooth gateway, or is it a searing wall of fire? Does information live on as a holographic ghost, or is it truly annihilated? The answer will rewrite our understanding of reality, forcing us to choose between the smooth continuity of space-time and the unyielding permanence of information. This is not merely an abstract debate. The fate of every star, every planet, and every bit of light that has ever vanished into a black hole's darkness hinges on the answer. The magnetic fields surrounding these cosmic remnants are so powerful they can warp reality itself. A magnetar, a special kind of neutron star, generates a magnetic force a quadrillion times stronger than the field that gently guides a compass needle on Earth. In the face of such an unimaginable force, the very atoms that make up matter are stretched and distorted. Their electron clouds, which normally form a fuzzy shell, are pulled into long, thin shapes, forcing atoms to line up in single-file chains. This is a one-dimensional world, a place where the rich chemistry of three dimensions is flattened into a stark and simple alignment. The magnetic grip is so absolute that it dictates the intrinsic spin of every particle, creating a strange, ordered substance that is utterly alien to our experience. This intense magnetism does not create a silent, frozen world. It builds up titanic stresses within the star's solid crust, a crust under unimaginable strain. When these stresses finally break, the star experiences a starquake, a seismic event on a cosmic scale. The crust cracks and shifts, releasing a cataclysm of energy. In a mere tenth of a second, a single giant flare from a magnetar can unleash more energy than our sun will emit over 100,000 years. For a brief moment, this flare can outshine every star in our entire galaxy. A blinding flash that is a direct result of matter wrestling with an impossible magnetic field. This dynamic and often violent relationship shows us that in the most extreme corners of the universe, matter is not just crushed. It is magnetically sculpted, torn apart, and reborn in flashes of energy that defy belief. The ultimate fate of matter under these immense pressures is written in a language of mathematics called the equation of state. This is not a single, simple formula. It is a complex relationship that describes how matter pushes back when it is squeezed, linking its pressure, density, and temperature. For a neutron star, this equation dictates everything. It determines how massive such a star can become before it surrenders to gravity and collapses into a black hole. It sets the star's final radius, defining whether it is a compact 20 kilometers across or a more spread out 30. Yet, despite its importance, this equation remains one of the greatest unknowns in physics. We simply cannot build a laboratory on Earth that can crush matter to such an extreme. Our most powerful particle colliders only give us a fleeting glimpse, a tiny sample of these conditions for a fraction of a second. So, to test our theories, we must look to the cosmos for natural experiments. A revolutionary moment came in August 2017, when observatories detected gravitational waves from a cataclysm over 100 million light-years away. This event, known as GW 170817, was the collision of two neutron stars. The ripples in spacetime it produced carried a hidden message. By analyzing the precise shape of these waves, scientists could infer the properties of the merging stars, gathering crucial data to rule out some theoretical equations of state and support others. This cosmic crash provided a direct test, a way to listen to the behavior of ultra-dense matter itself. The fundamental question we are trying to answer is stark. At the very core of a neutron star, does matter become a perfect superfluid, flowing without a hint of friction? Does it crystallize into a solid crust of exotic, hyper-dense nuclei? Or does the crushing force break the neutrons apart, creating a soup of their constituent quarks, a state of matter not seen anywhere else in the universe? Pinpointing the correct equation of state is the key that will unlock the hidden heart of these stellar remnants. It will tell us not only what they are made of, but also how they are born, how they live, and how they ultimately die. The known universe is built from the matter we can see and touch, but this is only a fraction of the whole story. Woven through the cosmos is a far greater presence, the invisible fabric of dark matter. Its nature is one of science's grandest puzzles, yet its behavior near the most extreme objects could be the key to unlocking its secrets. What happens when this unseen substance encounters the ultimate gravity of a black hole or the impossible density of a neutron star? Some theories propose that dark matter could be drawn into vast, invisible halos around these objects, slowly accumulating over billions of years. This hidden reservoir could subtly influence how a black hole spins or how a neutron star cools, altering their evolution in ways we are only beginning to model. The gravitational pull from a dense core of dark matter at the heart of a star remnant could even create a unique signature, a slight wobble in the signal from a pulsar that betrays the presence of something we cannot directly see. Other ideas are more dramatic. Certain models suggest that when dark matter particles are densely packed, they might annihilate upon contact, converting their mass into a flash of gamma rays or other exotic radiation. We are actively searching the skies for these precise signals emanating from regions near neutron stars and the supermassive black holes at galactic centers. Finding such a signal would be a monumental discovery, a direct message from the dark sector of the universe. This is the profound connection these cosmic laboratories provide. They force the known and the unknown to interact. By watching how dark matter behaves or fails to behave under the most demanding conditions gravity can create, we are conducting a grand experiment. We are testing whether dark matter interacts with itself or with normal matter through any force besides gravity. Each observation, each unexplained glitch in the rhythm of a pulsar, or each unusual burst of energy from a void, brings us closer to answering a fundamental question. Is dark matter a sea of ghostly particles that merely passes through everything? Or does it have a rich, complex physics of its own, waiting to be revealed in the shadow of these cosmic titans? These swirling disks of superheated plasma are the final furious whirlpools for matter falling toward the abyss. As gas and dust spiral inward, they do not plunge directly in. Instead, they orbit at fantastic speeds, colliding and generating immense friction. This friction heats the material to temperatures of millions of degrees, transforming it into a fourth state of matter known as plasma, a seething, electrically charged soup of atomic nuclei and free electrons. But friction alone cannot explain the incredible energy we see. The true engine of this cosmic vortex is a complex interplay between the plasma and magnetic fields, a branch of physics called magnetohydrodynamics. The swirling, conductive plasma drags and twists magnetic field lines, winding them into incredibly tight coils. These magnetic fields then act like cosmic rubber bands, snapping and transferring tremendous energy back into the plasma, further heating it to even more extreme temperatures. This process is so efficient that it causes the entire disk to glow with a ferocious light, emitting everything from radio waves to visible light to blistering X-rays and gamma rays. The energy released can outshine entire galaxies, making these accretion disks the most powerful persistent engines in the universe. From this chaotic maelstrom, something even more spectacular can emerge. Along the rotational axis of the system, perpendicular to the disk itself, magnetic fields can funnel some of this superheated plasma and launch it into the void. These are relativistic jets, narrow beams of particles accelerated to nearly the speed of light. They can stretch for thousands of light years across interstellar space, punching through galaxies and delivering energy to the most remote cosmic voids. By studying the light from these brilliant disks and their accompanying jets, we are essentially reading the operational manual for cosmic engines. Every flicker in an X-ray binary, every pulse from a distant quasar, is a coded message about how matter behaves in its final moments under gravity's absolute rule. This understanding transforms the way we see the night sky. That faint, twinkling point of light from an active galactic nucleus is not a serene star. It is the visible signature of a vast, spinning disk of incandescent plasma. A cosmic hurricane where magnetic storms rage and matter is forged into light before vanishing forever into the dark. From the depths of space comes a flash of radio energy more powerful than a billion suns, a signal that vanishes in less than the blink of an eye. These are fast radio bursts, some of the most fleeting and energetic phenomena we have ever detected. In a single millisecond, one of these bursts can release more energy than our sun will emit over 80 years. A cosmic shout from a distant galaxy that is over almost before it begins. The source of these immense, rapid-fire signals remains one of astronomy's most compelling puzzles. The leading suspects are the cosmic powerhouses we have already explored, magnetars and other ultra-dense objects. Imagine the crust of a magnetar, under unimaginable strain from a magnetic field of almost impossible strength. A sudden starquake, a fracture in that solid, dense surface, could release a cataclysmic jolt of energy, shaking the star's magnetic field like a bell. This violent event, known as magnetic reconnection, could snap magnetic field lines and reconfigure them in an instant, converting that pent-up magnetic energy into a blistering wave of radiation that we perceive as a fast radio burst. Other theories suggest the chaotic environment of an accretion disk could be the culprit. Here, vast clouds of plasma could become unstable, collapsing in on themselves or interacting with the central object's magnetic field to create a sudden, focused blast. The key to understanding these bursts lies not just in their incredible power, but in their brevity. Whatever creates them must operate on a timescale of milliseconds, implying a source that is incredibly compact, likely no larger than a few hundred kilometers across. This size constraint points directly to the realm of neutron stars and black holes. By capturing and analyzing these split-second signals, astronomers are using them as probes to study the most extreme environments in the universe. The radio waves travel for billions of years to reach us, and during their journey, they pass through clouds of ionized gas and dust. By measuring how the burst's different frequencies are dispersed and delayed, we can map out the invisible material that lies between galaxies, the cosmic web that structures the universe. Each burst is a brief, brilliant flare that illuminates the darkness, not just with its own light, but by revealing everything it has passed through. Unlocking the mystery of what creates these flashes will do more than just add a new entry to a catalog of cosmic events. It will reveal a fundamental, and perhaps violent, process by which matter and energy interact under the most severe conditions imaginable. These millisecond mysteries are forcing us to reconsider what is possible in the hearts of the universe's densest objects. Even the fundamental laws of heat and energy transform under this extreme pressure. The elegant rules of thermodynamics, which govern everything from a steaming cup of coffee to the life cycle of stars, are rewritten in the crucible of an accretion disk. Here, temperatures soar to billions of degrees, creating a plasma so hot that particles collide with ferocious energy, achieving a searing thermal equilibrium in mere instants. Yet, this classical balance is constantly disrupted. The bizarre rules of the quantum world introduce tiny but critical fluctuations, deviations that allow for processes which should be impossible, like particles tunneling through energy barriers to fuel even more exotic reactions. This strange marriage of the intensely hot and the infinitesimally small means that the very concept of temperature becomes a complex dance between vast forces and tiny probabilities. The most profound connection, however, lies with the black hole itself. These cosmic voids, once thought to be perfect absorbers, are now understood to possess both a temperature and a staggering amount of entropy. Entropy is the measure of disorder in a system, the universe's natural tendency toward chaos. A black hole represents the ultimate state of disorder, having shredded the complex information of everything it has consumed into an apparently featureless state. Its entropy is directly proportional to the surface area of its event horizon, a finding that stitches together the worlds of gravity, quantum mechanics, and thermal science into a single, startling framework. This implies that the horizon itself holds a phenomenal density of information, a hidden structure that defies our classical expectations. The laws of thermodynamics, when applied to these dark objects, suggest they must emit radiation and slowly evaporate over cosmic timescales. This forces us to confront the ultimate fate of organized matter. Does all the intricate structure of a star, a planet, or a living world ultimately descend into the featureless, high-entropy state of a black hole? Or does that information somehow persist, encoded on the boundary of the void? The behavior of thermodynamics in these extreme environments is not just a curiosity. It is a powerful clue, pointing toward a deeper, more complete theory of physics where the flow of energy, the arrow of time, and the very fabric of spacetime are inextricably linked. Gravity feels like the weakest of nature's fundamental forces. A simple refrigerator magnet can overcome the entire gravitational pull of our planet, lifting a paperclip with ease. This puzzling imbalance is known as the hierarchy problem, and it asks why gravity is so incredibly feeble compared to the electromagnetic force or the nuclear forces that bind atoms. The answer may be hiding in plain sight, within the very cosmic laboratories we have been exploring. In our everyday world, gravity is a whisper, but in the realm of ultra-dense objects, it becomes a roar, overwhelming every other interaction. This dramatic shift is the key. Could it be that gravity only appears weak because we are observing it from the wrong environment? Some of the most compelling theories in physics suggest that gravity's true power is diluted across realities we cannot perceive. They propose the existence of tiny, curled-up extra dimensions, realms far smaller than an atom. In our large, four-dimensional world, gravity spreads out and seems weak. But in the extreme, microscopic vicinity of a singularity or within a neutron star's core, these hidden dimensions could become significant, amplifying gravity's influence to finally match the strength of the other forces. This is not just a mathematical curiosity. We can search for its signature. When two neutron stars or black holes spiral together and merge, the resulting gravitational waves carry an imprint of how space and time vibrate. If extra dimensions are at play, they would subtly alter the ringing of spacetime after the collision, a deviation our observatories might one day detect. Similarly, if a black hole evaporates through Hawking radiation, the specific spectrum of particles it emits could reveal the hidden geometry of reality at the smallest scales. Solving the hierarchy problem would do more than just explain a number. It would build a bridge between the two great pillars of modern physics. It would connect the quantum world of the impossibly small with the cosmic realm of the impossibly large, revealing a unified landscape where all forces are, at their heart, different manifestations of a single, underlying truth. The crushing density of a compact object is not an end point. It is a window into this deeper symmetry, a place where the universe's most fundamental architecture is laid bare for those who know how to look. We are no longer just silent observers of the cosmos. We have learned to listen. The detection of gravitational waves has given us a new sense, allowing us to hear the faint tremors in spacetime itself. These ripples are born from the most violent events in the universe, the collisions and mergers of black holes and neutron stars. Each wave is a complex message, a cosmic chord that encodes the story of its origin. By carefully deciphering this signal, scientists can extract astonishing details about the objects that created it, their masses, their furious spins, and even the internal structure of neutron stars. This is how we test the equation of state, that fundamental description of matter under pressure without ever touching a sample. When two neutron stars spiral together, the gravitational waves they produce carry a unique signature of their final moments. The way they deform each other, the tidal forces that stretch them, all of this is imprinted on the ripples that travel across the universe. A softer star, one that is more easily squished, will create a different wave pattern than a harder, more rigid one. It is like listening to a bell ringing. By analyzing the sound, you can learn about the bell's shape and what it is made of. We are doing the same, but with stars. Future observatories, both on the ground and in space, will amplify this new sense. They will tune into fainter, more distant signals, perhaps catching the merger of a neutron star with a black hole, or even the collision of objects we have not yet imagined. Gravitational wave astronomy lets us hear the universe's most extreme laboratories in action, giving us a direct line to matter pushed to the very brink of existence. This firewall paradox presents a stark and violent choice for physics. To save the sacred rule that information cannot be destroyed, we might have to sacrifice one of Einstein's most cherished principles. The principle of equivalence, a cornerstone of general relativity, assures us that a person in free fall would feel nothing unusual as they cross the event horizon. There would be no abrupt jolt, no searing heat, only the smooth, silent continuation of their journey into the unknown. The firewall hypothesis shatters this elegant picture. It proposes that the horizon is not a silent gateway, but a blistering wall of energy. Any object approaching it would be instantly vaporized by a storm of high-energy particles, a fate so absolute it would resolve the information paradox by ensuring nothing, and therefore no information, ever actually enters the black hole. Yet this solution feels like a desperate compromise. It saves one law of physics by blatantly breaking another. It trades the smooth, continuous fabric of spacetime for a cosmic kill zone. So, which is it? Is the event horizon a place of no drama, as Einstein's theory insists, or is it the most dramatic and final boundary in the entire universe? The answer forces us to question the very nature of the reality we think we understand. If a firewall is real, then our conception of black holes as smooth, geometric structures is fundamentally wrong. They would be objects cloaked in a layer of pure chaos, and the journey of matter would end not in a mysterious crush, but in a definitive flash of light. If firewalls are not real, then we are back at the beginning, staring into the paradox and wondering where the information goes. This is not an abstract debate. It is a battle for the soul of physics, fought on the edge of a shadow. Even the deepest connections in the universe are tested at the edge of a black hole. The bizarre phenomenon of quantum entanglement creates a bond between two particles so profound that a change to one instantly influences the other, no matter how far apart they are. This ghostly link seems to defy our everyday understanding of space and distance, and it may be the key to solving one of our greatest cosmic puzzles. In the chaotic environment just outside a black hole's event horizon, where particles are constantly being created and torn apart, some theories suggest that particles can become entangled across the ultimate boundary. One member of the pair falls into the abyss, while the other escapes into the universe. If this connection holds, it could provide a secret channel, a way for information about what fell in to be imprinted onto the radiation leaking out. This idea offers a potential escape from the information paradox, suggesting that the data is not lost forever but is instead transmitted through this quantum code, slowly unraveling the black hole's secrets as it evaporates. The survival of entanglement in such a violent place is itself a marvel. The immense gravitational tides that spaghettify matter might be powerless to break this quantum link. It is a connection that exists outside of space-time, a thread that does not break no matter how far it is stretched. This reveals a startling form of resilience, showing that even in the most isolated and destructive environments, a fundamental interconnectedness persists. The exploration of these quantum correlations is forging a new bridge between the science of the impossibly small and the physics of the impossibly large. By asking how information is preserved in the most extreme conditions, we are discovering that no object, not even a black hole, is ever truly an island. Its story may be written in the silent, instantaneous language of particles talking to each other across the void. Long before the first stars flickered to life, the cosmos may have forged its own dark seeds. In the frantic, seething heat of the very early universe, tiny regions of space could have been squeezed with such immense pressure that they collapsed directly into black holes. These hypothetical objects, known as primordial black holes, are unlike any we have discussed. They were not born from dying stars. They are potential relics of the Big Bang itself, ancient artifacts that could have shaped everything that followed. If they exist, they would have been among the very first structures to emerge, forming when the universe was less than a second old. Their possible masses are staggering in their range, from lighter than a paperclip to heavier than 1,000 suns. This radical idea presents a compelling solution to two of astronomy's greatest puzzles. Could these primordial black holes be the invisible seeds around which supermassive black holes grew at the centers of galaxies? And even more profoundly, could they themselves be the mysterious dark matter that binds the cosmos together? The behavior of the first matter in the universe would have been violently sculpted by these objects. Imagine a hot, dense soup of fundamental particles suddenly finding itself orbiting a tiny, invisible pit of infinite gravity. The way this primordial plasma was pulled, heated, and compressed around these black holes could have dictated where the first stars and galaxies were able to form, setting the blueprint for the entire cosmic web we see today. Finding them, however, is a monumental challenge. They are likely dark and drifting through space, but we have ways to hunt for their ghostly presence. A primordial black hole passing in front of a distant star would act as a gravitational lens, bending the star's light and causing it to briefly and mysteriously brighten. Others might reveal themselves by feeding on the sparse gas of the interstellar medium, emitting faint, telltale X-rays. The discovery of even one primordial black hole would be a window directly into the universe's first moments. It would allow us to study how matter behaved under conditions of unimaginable density and temperature, a reality we can never recreate. These ancient shadows are more than just cosmic curiosities. They are potential keys to understanding the very first chapter of our cosmic story, a chapter written in the language of gravity and primordial fire. A cosmic dance between two stellar remnants creates a laboratory of unimaginable force. In a binary system, a neutron star and its companion, or perhaps two black holes, orbit one another in a close gravitational embrace. This proximity generates tidal forces of staggering power. If one of the objects is a normal star, the gravity of its dense partner can reach out and tear material directly from its surface. This stolen matter does not fall straight in. Instead, it forms a brilliant, spiraling river of gas known as an accretion stream, swirling into a disk of incandescent plasma around the waiting remnant. This entire system becomes a dynamic engine, its brightness flickering and flaring in response to the complex gravitational interplay. The variability we observe is a direct readout of matter being stretched, heated, and compressed in real time. These systems are prime sources for the gravitational waves we can now detect, the ripples in spacetime created by their orbital motion. They also blast out high-energy X-rays and gamma rays as the accreted matter is heated to millions of degrees. The magnetic fields of the neutron stars add another layer of complexity, channeling the plasma and often launching it into space in the form of focused, relativistic jets. By watching these binary dances, we are not just seeing two objects in orbit. We are witnessing the entire life cycle of matter in a coupled system, from the moment it is pulled from a star to its final fate, whether that is incorporation into the dense remnant or violent ejection back into the cosmos. This grand choreography reveals how stellar remnants evolve and influence each other, showing that even in isolation, no cosmic object is truly alone. True emptiness is a cosmic illusion. According to quantum theory, the vacuum of space is not a still and silent void. It is a vibrant sea of potential, a stage for a fleeting, ghostly dance. At every moment, pairs of virtual particles and their antiparticles spontaneously flicker into existence, borrowing energy from the universe only to collide and vanish back into nothingness an instant later. This ceaseless activity is usually perfectly balanced, leaving no trace behind. But near the event horizon of a black hole, this delicate balance is shattered by gravity's absolute power. In this chaotic borderland, a virtual particle pair can be torn apart before they have a chance to annihilate each other. One member of the pair falls across the boundary, forever lost to the black hole's interior, while the other is set free, escaping into the universe as a real particle. This steady trickle of escaped particles is Hawking radiation, a faint whisper of energy that slowly bleeds mass away from the black hole itself. This means black holes are not the eternal prisons we once thought they were. Over timescales that dwarf the current age of the universe, a black hole can slowly evaporate, fading away into nothing. This discovery transforms the vacuum from a passive backdrop into an active participant. The intense gravity of an ultra-dense object literally bends the fabric of this quantum sea, stirring it into a creative and destructive frenzy. The void itself becomes a dynamic force, capable of birthing real particles and ultimately dismantling the cosmos's most powerful objects. What does this say about the nature of nothingness? It reveals that emptiness is not simple. It is a rich, complex state, pregnant with possibility, and its character is fundamentally altered by the presence of immense gravity. This quantum activity challenges our most basic ideas about stability and permanence, suggesting that even the mightiest cosmic structures are subject to the subtle, persistent churn of the virtual world. These invisible experiments unfold not in a laboratory, but within the humming memory of supercomputers. Since we cannot travel to a neutron star or recreate its core on Earth, scientists build digital universes governed by the unbreakable laws of physics. They feed equations from general relativity and magnetohydrodynamics into these powerful machines, setting in motion virtual cataclysms that would be impossible to witness otherwise. With a click, two neutron stars are set on a collision course. The simulation calculates the result, modeling how their incredible densities warp spacetime, how their magnetic fields twist and snap, and how their very matter is torn apart and reformed. This digital recreation is what allows us to interpret the faint gravitational wave signals we detect from across the cosmos. The ripple in spacetime we recorded becomes a story, its plot revealed by comparing it to thousands of such simulated collisions. These models predict the brilliant kilonova explosions that forge heavy elements like gold and platinum, and they show how the chaotic debris can sometimes form a jet, a narrow spear of particles accelerated to nearly the speed of light. As computing power grows exponentially, the simulations gain breathtaking detail. They can now begin to incorporate the bizarre rules of quantum mechanics and the complex interactions of nuclear physics, painting a more complete picture of matter pushed to its absolute limit. This is more than just advanced video game graphics. It is a fundamental method of discovery, a way to run experiments on the universe's most extreme environments from the safety of our own planet, guiding our telescopes to know exactly what to look for next. A deeper law may protect the very fabric of reality from its own flaws. This is the core of the cosmic censorship hypothesis, a profound idea suggesting that nature abhors a visible singularity. Proposed by the physicist Roger Penrose, it argues that every point of infinite density, the chaotic heart of a black hole where physics breaks down, must be permanently veiled by an event horizon. Think of this horizon as a cosmic curtain, drawn shut to hide the unpredictable madness backstage. If this curtain were to tear, the singularity would be exposed as a naked singularity, a point of infinite gravity with no shield, and its bizarre influence would spill out into our universe. The rules of cause and effect, the reliable predictability that allows us to trace a planet's orbit millions of years into the future, would utterly collapse. The deterministic nature of physics, the idea that the past dictates the future, would be replaced by random, uncontrollable chaos. Yet the mathematics of Einstein's own general relativity does not strictly forbid such a monstrosity. Some solutions to his equations allow for these naked singularities to theoretically form, perhaps from the direct collapse of certain types of matter or from the violent merger of two black holes. What would happen if you encountered one? The laws of physics as we know them would offer no guide. Time could loop backwards, gravity could become repulsive, and matter might be reconfigured into forms beyond our imagination. The very geometry of space would become unpredictable from one moment to the next. Determining whether cosmic censorship is a true law of nature is therefore one of the most urgent quests in theoretical physics. It asks a fundamental question about our universe. Is the cosmos inherently orderly, with built-in safeguards that protect us from its own most extreme creations? Or is reality ultimately unpredictable at its deepest level, with the potential for absolute chaos lurking just behind a fragile veil? The answer defines the limits of our understanding and the ultimate predictability of the cosmos itself. Each new window we open onto the cosmos reveals a different facet of the story. Our eyes alone see only the narrow band of visible light, but the universe broadcasts its most dramatic events across the entire electromagnetic spectrum. To understand the violent processes near black holes and neutron stars, we must listen to every channel. Radio telescopes map the vast, swirling structures of relativistic jets, while infrared observatories peer through cosmic dust to witness the birth of stars from their remnants. X-ray and gamma-ray telescopes are perhaps the most crucial for this work, capturing the blistering emissions from million-degree accretion disks and the colossal flares from Magnetar starquakes. Each type of light is a different language, telling us about temperature, magnetic field strength, and the speed of infalling matter. But light is only one messenger. The historic detection of gravitational waves opened an entirely new sense, allowing us to feel the subtle ripples in spacetime itself. Ground-based observatories like LIGO and Virgo have tuned into the high-frequency chirps of colliding black holes and neutron stars. These signals provide a direct, non-electromagnetic measure of these events, revealing masses and spins with stunning precision. The future promises an even richer auditory experience. The Laser Interferometer Space Antenna, or LISA, is a planned mission that will operate in the quiet of space. Freed from Earth's seismic noise, it will detect the low-frequency rumble of supermassive black holes merging at the hearts of galaxies, a deep bass note to complement LIGO higher-pitched discoveries. There is a third, even more elusive messenger. Neutrinos, the ghostly particles that barely interact with anything, could provide a direct probe into the heart of a neutron star. These particles are born in the intense nuclear reactions within these dense cores, and they can fly straight out, carrying information about the star's internal composition without being scattered or absorbed. Catching them requires enormous, sensitive detectors buried deep underground, like the Ice Cube Observatory at the South Pole. A neutrino flash from a nearby neutron star merger would be a priceless telegram from the very edge of matter's endurance. Every technological leap, from a new telescope to a more sensitive wave detector, acts like a new key unlocking a different door in the cosmic laboratory. We are no longer just watching the universe. We are listening to its vibrations and feeling its most energetic particles. This multi-messenger approach, combining light, waves, and particles, is weaving a complete picture of how matter behaves when pushed to its absolute limit. With each new instrument, we refine our models, discard old theories, and catch a glimpse of a deeper, more fundamental truth waiting just beyond our current understanding. The universe might be a magnificent illusion, a cosmic hologram. This is the startling claim of the holographic principle, an idea that reimagines the very nature of reality. It suggests that all the information describing the three-dimensional world around us, every star, every person, every bit of matter falling into a black hole, is not stored within the volume of space itself. Instead, it is perfectly encoded on its two-dimensional boundary, like a shimmering pattern of data on a vast, spherical movie screen. Think of a credit card hologram, a flat sticker that creates the convincing illusion of a three-dimensional object floating in space. The holographic principle applies this same logic to the cosmos, proposing that our rich, voluminous reality is a projection from a thin, distant shell of information. For a black hole, this shell is the event horizon. When matter crosses this threshold, it does not simply vanish into a singularity. According to this view, its information is instantly smeared and scrambled across the surface of the horizon, preserved forever as a kind of cosmic fossil. The three-dimensional object is gone, but its complete blueprint remains, etched onto the boundary of the void. This offers an elegant solution to the information paradox, suggesting that data is never truly lost, only translated into a different holographic language. If this principle holds for a black hole, could it be true for our entire universe? Some physicists speculate that we are all living inside a holographic projection, that the dance of galaxies and the behavior of matter in the most dense regions are just shadows cast by a more fundamental, lower-dimensional reality playing out on the edge of the cosmic stage. This idea bridges the chasm between quantum gravity and string theory, suggesting that the bizarre laws of the very small are simply the native language of the universe's true, lower-dimensional surface. Exploring the holographic principle forces us to confront a profound possibility. The solidity of the world, the very essence of matter and space, might be an emergent property, a secondary effect born from a vast, interconnected network of information. The next time you look up at the stars, consider that you might be seeing a magnificent projection, a cosmic code written in light on the inside of a sphere we can never see. These cosmic engines are the architects of the universe itself. The collisions of black holes do more than send ripples through space-time. They build the foundations upon which galaxies are formed. When two black holes merge, the resulting, more massive object sinks to the gravitational center of a galaxy, becoming a supermassive anchor. This central presence governs the motion of billions of stars, shaping the grand spiral arms and elliptical halos we see across the cosmos. A galaxy's very structure is carved by the silent, dark heart at its core. But the creation does not stop with gravity's architecture. The most spectacular alchemy occurs when two neutron stars spiral together in a final, violent embrace. In the incandescent fireball of their collision, conditions become so extreme that neutrons are captured at a frantic rate, forging the heaviest elements in the universe. The gold in a wedding ring, the platinum in a catalytic converter, and the uranium that fuels reactors were all born in these cataclysmic explosions, scattered across space to be incorporated into new stars, planets, and eventually, life. The energy released in these events is a cosmic force of both life and death. A tremendous outflow of radiation from an active galactic nucleus can blow away the gas clouds that would otherwise collapse to form new stars, effectively quenching star birth in a region for eons. Conversely, the shockwaves from a supernova can compress nearby gas, triggering the birth of a new generation of stars. This intricate feedback loop, governed by the behavior of matter at its most extreme, dictates the rhythm of stellar life and death. Every time we look at the night sky, we are witnessing a universe shaped by these transformative processes. The distribution of galaxies, the very chemistry that makes our world possible, and the large-scale cosmic web are all a direct result of what happens in the fierce, dense hearts of these celestial powerhouses. Deep within a neutron star's heart, matter may surrender its familiar identity entirely. The neutrons themselves, under such unimaginable pressure, could shatter into their constituent parts, creating a soup of free quarks and gluons. This is the fabled quark-gluon plasma, a primordial state of matter that has not existed freely since the first microseconds after the Big Bang. Here, in this dense core, it might persist as an exotic, ultra-dense fluid. Some theories go even further, suggesting this quark soup could cool and organize into a color superconductor, a frictionless medium where certain quark pairs flow with perfect efficiency. The stability of these bizarre states is one of the great unknowns in physics. Are they a final, stable endpoint for compressed matter, or are they merely a temporary, metastable phase? A sudden shift from one state to another, a phase transition in the core, would be a cataclysmic event for the entire star. Imagine the ground beneath your feet instantly turning to ice, then just as instantly flashing into steam. On a neutron star, such a transition would release a colossal amount of energy, potentially cracking the star's solid crust in a massive starquake and triggering a brilliant gamma ray burst visible across the universe. This could be the violent engine behind some of the most powerful explosions we detect. The ultimate collapse, where the core's exotic matter can no longer support the star's weight, and it implodes into a black hole, would send a unique tremor through space-time. The resulting gravitational wave signal would not be the clean chirp of two black holes merging, but something richer and more complex, carrying the imprint of the star's internal structure in its final, desperate moments. By listening for these signals, we are essentially taking the temperature and pressure of these hidden realms, slowly mapping out the phase diagram for matter at supranuclear densities. This is not just about stellar anatomy. It is a direct probe into the fundamental forces that govern all reality, a quest to understand the very limits of material existence and the ultimate fate of matter in the most extreme environments the universe can create. Our journey into the heart of cosmic extremes reveals a universe far stranger than we ever dreamed. We have seen how gravity's absolute rule near black holes and neutron stars shatters our everyday expectations, stretching matter into streams, forging impossible substances, and bending the flow of time itself. These are not just distant curiosities. They are natural laboratories where the fundamental laws of physics are tested to their breaking point, forcing us to rewrite the textbooks. The quest to understand what happens inside a neutron star's core or at the edge of a black hole's event horizon does more than satisfy our innate curiosity. It propels our technology forward, driving the creation of unimaginably sensitive detectors and powerful supercomputers that can simulate these cataclysmic events. Each new observation, whether a ripple in space-time or a flash of gamma rays, is a piece of a grand cosmic puzzle. As we continue to peer into these ultimate frontiers, we move closer to answers that could unite our understanding of the very large and the very small. The universe is a testament to boundless wonder, and its greatest secrets are still waiting in the dark. We would love to hear which of these cosmic mysteries captivates you the most. Share your thoughts in the comments and never stop looking.